Hey everybody, I wanted to walk you through ChemActivity letter K, Intermolecular Forces. And this walks you through part of the Spartan software, which I have some screenshots included so that you can see what they're trying to demonstrate there. If you would go ahead and pay attention to this. So first of all, this calls for you to come up with a couple of molecules. And the first molecule that you're coming up with, ethanol, and it walks you through the sequence. First, what you're doing is you're making your sp3 hybridized carbon right here, and then you're adding another carbon to it. You're making 2 ethanol molecules, then 4 ethanol molecules. I'm going to shorten that ETOH, and then finally you're going to have a total of 8 ethanol molecules. Now with those 8 ethanol molecules, what you're going to do is you're going to do a little bit of a simulation. So once we have all of these different ethanol molecules that we can look at, one of the things that we're asked to do is to look at an animation of how these ethanol molecules that we've originally designed, how do they reorient themselves into a most energetically favorable position. And the way that we can see that is with this little video animation. What's being obscured by my face right now is there is a little button that shows clicking for lowest energy model. Okay, so press that button and all of those ethanol molecules bounce all around. And ultimately they reach a place where they are most stable and they are farthest away from one another. The next part of this procedure asks you to go ahead and look at once those molecules are all organized, to go to a pull down menu and to define hydrogen bonds. Okay, and so what I've done is I've shown a screenshot of those hydrogen bonds, or prior to those hydrogen bonds being in place, but then what are these bonds or where do they actually appear? And so what I'm going to do is circle an example of a hydrogen bond. Okay, so these are bonds between all of the different ethanol molecules, and so that makes them intermolecular rather than intramolecular. So intermolecular between different molecules, and intramolecular are bonds within a single molecule. And so intramolecular bonds are what we've been consistently talking about this semester, but now we're introducing this concept of intermolecular. And so this is an example of a hydrogen bond. What I want you to see is this molecule right here, that's one ethanol molecule, and here's an adjacent ethanol molecule. And what we have is a hydrogen right here on one molecule and an oxygen on an adjacent molecule. And we see these hydrogen bonds indicated by these dashed green lines. And that's something that is definitely worth recognizing, because that is a force that holds kind of 2 molecules in close proximity to one another. So the good definition, or a good definition of a hydrogen bond, is the attractive force between an electronegative atom, specifically fluorine, oxygen, or nitrogen, of one molecule, and a hydrogen atom that is bonded to an electronegative atom on a different molecule. Okay, so the way that we could kind of see that is here. I'm going to go ahead and draw an ethanol molecule, CH3, CH2, then we have an oxygen and a hydrogen. Now this oxygen has 2 lone pairs of electrons, so I'm going to use a different color to show the hydrogen bond, or sorry, the other molecule that's involved in this hydrogen bond. And I'm going to draw it a little bit differently, but it's the same molecule. So we have HOCH2CH3. Okay, so this right here, this kind of interaction between my hydrogen of one atom, or I'm sorry, of one molecule, and the oxygen of another molecule, that would be a good example of a hydrogen bond. Now notice that this other ethanol also has those oxygens an oxygen with those lone pairs of electrons, so that would be a good candidate for further hydrogen bonding. Hydrogen bonding ultimately is kind of a very strong and powerful force, because you have lots of different interactions taking place between individual molecules. Our next type of interactions are dipole-dipole interactions. These are intermolecular, again, intermolecular between two or more molecules, attractions that form between polar molecules. And a good example of this is the type of interactions that take place between adjacent HCl molecules. Now, hydrochloric acid, we know that's a strong acid, HCl. And what we know about each of these atoms is that hydrogen is going to be a partial positive charge and chlorine is going to be a partial negative. So we have these charges, I'm sorry about that, that allow kind of attraction between adjacent molecules. So with HCl, what we're going to have is between different molecules, we're going to have the hydrogen and the chloride of adjacent molecules that are attracted to one another. Now, it's worth noting that this is a hydrogen involved, but this is not hydrogen bonding. Now, to contrast that, if you had something like HF, well, what do we know about fluorine? One thing that we know about fluorine is it is extremely electronegative. And so what we also know about fluorine is that it is one of the atoms that is commonly involved in hydrogen bonding. And so this right here is hydrogen bonding. And so the difference between these is the actual atoms that are involved, fluorine versus chlorine. Now, fluorine is so much more electronegative that it reaches that electronegativity threshold that is going to kind of institute, or it's going to consider, or it's going to make HF versus HCl, HF be involved in hydrogen bonding, whereas HCl is not. Okay, our last example of an intermolecular force is dispersion forces. You might also know these as London forces or London dispersion forces. And what these are kind of an induced or a temporary dipole. Now, these are the forces that take place between molecules, and I think an easy example of these taking place between individual atoms would be something like helium. Helium has 2 electrons, and if we draw a single helium atom, we've got our 2 electrons floating around in there, and if they are evenly floating around, well, then it's going to have an evenly distributed negative charge. Now, if, however, at some point, because these electrons are constantly moving, if these 2 electrons end up over here, that means this side of that atom is going to be negatively charged and this is going to be partially positively charged. And so that's why this is a temporary dipole. You would have something that is a temporary positive charge and a temporary negative charge, but that can cause the actual interaction between different molecules. And so if you take something like CH4, well, CH4, you've got no dipole moment. All of these charges, or all of these bonds basically offset one another. Well, you do have some sort of interaction between adjacent CH4 molecules, though, and these interactions are not going to be, when it comes to intermolecular forces, it's obviously not going to be ionic interactions, not going to be a dipole-dipole interaction, nor would it be hydrogen bonding. Instead, these CH4 molecules are going to be, there is force between them, but it is in the example of a dispersion force or a temporary dipole. Okay, so now let's take a look and compare some of these different molecules and ultimately what they can mean. So if we took a look at a couple of different molecules, and for this we're going to go ahead and look at 3 different molecules: methane, CH4, then CH3Cl, and finally CH3CH2OH. Okay, if we look at these 3 different molecules, and if we kind of look at the structure of them, H, 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 H. Let's consider the types of interactions that can take place between them. And not between like the CH3Cl and CH4, but instead if we have multiple copies of CH3Cl, we have multiple copies of CH3, CH2, OH. So if we have lots of copies of each one of these, what types of interactions are going to be taking place between them? Now, what you can first ask yourself is this molecule polar? So this is a non-polar molecule. So methane, for example, has no dipole moment. No dipole. And so the types of interactions that are going to take place between CH4 and other CH4 molecules, well, they're going to have to be those dispersion forces. And one thing that you see about multiple methane molecules and physical properties of a methane solution is that the boiling point of that solution is negative 161 degrees Celsius. So these molecules are not held together very tightly, and so that solution is going to boil. It's going to vaporize at a very, very low temperature. Now, if you compare that to something like CH3Cl, well, this is a polar molecule, and so you could imagine that there's a obvious partial negative charge, and then your carbon could carry that partial positive charge, for example, but you've got basically a dipole moment to this molecule. Now, is that going to include these sorts of interactions that would, or does it have the criteria, does it meet the criteria for hydrogen bonding? Hydrogen bonding, we need an electronegative element like nitrogen, oxygen, or fluorine. Well, CH3Cl does not have that, in which case your types of interactions between them are going to be dipole. The way that I kind of think about dipole interactions are, they're a type of force that are strong, that can attract molecules to one another, but they're just not quite as strong as hydrogen bonds. Okay, so, or hydrogen bonding. And so one of the things that you see is this solution has a boiling point of negative 24 degrees Celsius. So a lot less heat is required in order to get this solution to boil compared to a methane solution, but it's still not a particularly high amount. Now, if we think, now our last molecule, CH3CH2OH, this is commonly known as ethanol, and one of the things that you notice about this is this has been our example for a molecule that is capable of hydrogen bonding. So we have hydrogen bonding that can take place between multiple CH3CH2OH molecules. And one of the ways that that ultimately plays out is the boiling point for ethanol is about 80 degrees Celsius. So the interactions that take place between these individual molecules have an overall impact on that solution, or an overall impact on that substance. So it's important to be able to look at a substance or look at a compound and determine what type of interactions are taking place between the multiple copies of that compound or of that molecule. So if we look at two different molecules, H3COCH3. This molecule has a lone pair of electrons, or two lone pairs of electrons on that central oxygen. Now, if we compare that to this molecule right here, HNHC, H. Okay, now if we compare these two molecules, one of the things that's worth noting is they definitely both do have oxygens with lone pairs of electrons, but those oxygens are a little bit different. So on our molecule over here, this is an example of an ether. Okay, now what we have is a lone pair of electrons. I think I can improve my drawing there a little bit. We have an oxygen that is bound to two carbons. Okay, both of those carbons are basically equal to one another. Now, is this molecule a polar molecule? Yes, it is. This molecule is a polar molecule, and you've got a partial positive charge and a partial negative charge on it. That partial negative charge is near that lone pair of electrons, so we've got a dipole moment that looks a little bit like this. Okay. Now, on the other hand, our other molecule, let's compare our oxygens. We've got one that has a double bond and two lone pairs of electrons, and then one that's a single bond that's bonded to an oxygen. Or I'm sorry, that's bonded to a hydrogen. What else do we have? Well, we've also got a nitrogen that's got a lone pair of electrons. One of the criteria that we're looking for whenever we're trying to determine what type of forces are interacting or are involved in the interaction between molecules is we want to find a lone pair of electrons. And whenever we look at this, we see a lone pair of electrons, and we see it on a nitrogen, and we see our lone pairs of electrons on oxygens. Okay. Now, if you think back to hydrogen bonding, you want to see a lone pair of electrons on a nitrogen, oxygen, or a fluorine. So does this fit that criteria? Yes, it does. Okay. Now, does this fit that criteria? Yes, it does. We've got a lone pair of electrons on our oxygens. What makes that molecule here on the left-hand side, our ether molecule, a little bit more complicated is we have that dipole, but we don't have any hydrogens already bound to that oxygen. So in our molecule on the right here, we've got a hydrogen bound to a nitrogen with a lone pair of electrons. Okay. We've got an oxygen with a lone pair of, or two lone pairs of electrons and a bond to a hydrogen. So which one of these would be a good criteria for hydrogen bonding? Well, this molecule right here. This one, well, it's going to be strongly held together, but this is going to be held together through dipole-dipole interactions. So whenever you're thinking about identifying what type of forces exist between molecules, start out with your criteria for hydrogen bonding. You've got to find a nitrogen, oxygen, or a fluorine, and you've got to find a hydrogen bound to that. Okay, so if you don't find that nitrogen, oxygen, or fluorine, well, then you know that it's not going to be hydrogen bonding. It's also likely not going to be, it's not going to be hydrogen bonding, and there's a chance that it might not be a dipole-dipole interaction. If you see something, but look and find out if that is a polar molecule. So if you have something like this, we've got a bunch of carbons and hydrogens. We don't really have a pole to that, so that's not going to be a polar molecule. And so this is going to be held together by London forces. And I was able to do that simply by identifying, or first by asking my question of, do I have any nitrogens, oxygen, or fluorines in there? And then, if the answer is no, then I can say, okay, well, what else do I have in there? All I've got are carbons and hydrogens. This is not a polar molecule, so are there going to be intermolecular forces? Yes, there are, but they're going to be London forces, which are the weakest of the forces. So once you've done that, use that as kind of your sequence. Go through, does it meet the criteria for hydrogen bonding? If the answer is no, does it meet the criteria for dipole interactions? If the answer is no, then it's going to be London forces that hold those molecules together. I hope this was helpful, and I hope you have a wonderful afternoon.